Hello, calculus students. It's good to be back again. Today's topic is the chain rule. As you may know, one way that you can build up complicated functions from simpler ones is through a process called function composition. Now, the chain rule is a rule that tells us how to differentiate these compositions, and it depends on you knowing how to calculate the derivatives of the component pieces. Another thing that the chain rule tells us is how the rates of change of the component pieces are related to one another. And this will be really important as we move into studying a kind of problem called a related rates problem.
Hello, calculus students. Today's topic is the chain rule. So what's the chain rule? What's it good for? Well, it's a pretty important rule, and the two big uses of it are, one, we use it to calculate compositions of functions. So whenever one function, has been sort of put inside of another function. We've seen compositions of functions before, but just to remind you, we might be wanting to calculate the derivative of some function like f of x equals square root of x squared plus 1. How would you calculate the derivative of that? At this point, we don't know how, but with the chain rule, we will know how. And the second thing that we do with the chain rule a lot is to understand what are called related rates. So understand rates of change between related variables. So it happens sometimes that as one variable changes, it causes another variable to change because they're interdependent on one another. And like just a quick little example, like let's say you have a situation where you got a temperature function t, and temperature is a function of height y. So t is temperature, and then y is height. So, as you know, when an object goes higher and higher, it gets cooler and cooler as you go up. And then maybe y, height, is a function of time. So y is there's some sort of, y is like a position function. So here t is time. And so then I might like to know, I might want to know is, how fast is the temperature changing with respect to time? In other words, I want to know what is the derivative of the temperature function taken with respect to time. What is d big T, d little t? It's a natural question to ask. What is how fast is the temperature changing at a particular moment in time? I might rather know what's happening with respect to time rather than what's happening with respect to the particular height it's at. So you see the variable that big T depends on y, in turn is dependent on the variable little t. So that means that big T is indirectly dependent on time. And so then the chain rule gives us a way to calculate that derivative big T d little t, even though the function big T has been given to us in terms of height rather than in terms of time. So that's the sort of thing we'll be able to get at with the chain rule. So without further ado, here is the chain rule. So the hypotheses of this theorem essentially say that the two functions are differentiable and, need to be differentiable at the appropriate points. So the function that you're wanting to differentiate is the composition, f of g of x. So you need the outside function f to be differentiable at the output values of the inside function. And then the inside function needs to be differentiable just for whatever x is. Right, so the chain rule tells us how to differentiate the composition of the functions. And I tend to you can use either formula for computation, but the first formula we tend to use more for looking at related rates. It gives us a good visual way to see how rates are related, whereas this one the second one we usually use for computing derivatives. So the chain rule, when you first see it, it's kind of an intimidating looking proposition, but you'll see with just a little bit of practice, just even an example or two, you'll see how it functions in practice. In practice, here's how I kind of think of it. So what the chain rule is telling you to do is to differentiate the composition f of g of x. You differentiate the outside function f, but you leave g of x inside of it. So if you leave g of x inside that outside function alone, then you multiply times the derivative of the inside function. It's kind of like this. If I want to take the derivative, maybe I should use prime notation. If I want to take the derivative of some outside function of some inside function like this, so the derivative of outside of inside is, it's the outside function's derivative, but you leave the inside stuff alone, but then you multiply times the derivative of the inside. So something like that. So let's have a look at an example or two to start getting a feel for it. So here I'm going to use that sort of second formulation of the chain rule that tells us that the derivative of f of g of x is f prime of g of x multiplied times g prime of x. So I'm using this formula right here. I'm going to really sort of spell out the details for the first couple of examples, but after you see it spelled out a few times, really you do it a lot quicker and with a lot less fuss. But we're going to make a lot of fuss at the beginning just to make sure we're getting it. All right, so we got this function h of x is the quantity 3x squared plus 4x to the 100th power, and we want to find the derivative. All right, h prime of x. Well, before we start just trying to calculate the derivative, let's identify what's our outside function. Well, the outside function is, raising something to the 100th power. So we could express that as f of x equals x to the 100th. And we can see an inside function of g of x equals 3x squared plus 4x. And you can see, you put these two together, your original function, 3x squared plus 4x to the 100th, certainly is f of g of x. Right, so now we have our outside function and our inside function. Now the chain rule says you need to know how to differentiate both the inside function and the outside function separately, right? Well, what is f prime of x? Well, that's easy. F prime of x is just 100 times x to the 99th using the power rule. And then from that, we can obtain what f prime of g of x is. See, we need that in the formula for the chain rule up there, right? Let me underline it in red here. So we need to figure out what f prime of g of x is. So since we know what f prime of just x is, then f prime of g of x would be just to put g of x in place of x in the formula for f. So that'd be 100. G of x is 3x squared plus 4x, and then that's raised to the 99th power, right? And then, of course, we can do g prime of x. G of x is 3x squared plus 4x, so g prime of x is 6x plus 4. And so now we know what, underlining in green here, we know what g prime of x is in the so now we have both of the pieces in red and green at the top that we need to calculate the derivative. At this point we'll have h prime of x, which is the same as taking the derivative of f of g of x. It's going to be your f prime of g of x, so it's 100 times 3x squared plus 4x to the 99th. Then you multiply that times the derivative of the g of x, so you get 6x plus 4, and that's your answer. So the key to it is you got to identify an outside function and an inside function, both of which you can differentiate fairly easily. And then you just got to remember that for the inside function, you're going to leave whatever was originally inside the outside function. You're just going to leave it that way on the inside of the function as you differentiate it. So in practice, if I was doing this derivative, I wouldn't be writing down all this. F of x is equal to this and g of x is equal to that. I would just do it, right? If I was doing the derivative of, what was our problem here? 3x squared plus 4x to the 100th power. In my mind, I'm just going to go, okay, the part that's on the inside here, just think of it as a single, like, in my mind, I just go think of as a single variable. So that I'm just going to treat it like it's an x, right? So if it were just like a single x, I would bring the 100 down, and then I would lower the power on that variable to the 99th. But then I say, hey, I got to remember by the chain rule, I have to take the derivative of the inside. So I multiply times the derivative of the inside, which is 6x plus 4. So you see, I can go straight to the answer just by paying attention to what's the inside and what's the outside. I want to do another example where I really make a big deal out of identifying different variables. And this time we're going to use the other formulation for the chain rule, the one that says dy dx equals dy du times du dx. Now you may notice in that formula that it looks like fractions are canceling. Like it looks like you could cancel the du's, right? And you'd be left with dy over dx. I guess technically you're not really supposed to think of it that way, but actually you can. Derivatives really are fractions. It's just we don't have a way to think about it properly yet. But in any event, so that helps you. That's sort of a way to remember if you're writing down the chain rule right. You always got to have this sort of canceling thing going on. So anyway, I want to try to use that form of the chain rule to calculate the derivative of this compound function here, y equals the square root of x squared plus 1. Kind of like before, you need to identify an outside function and an inside function. And the difference is here, the outside function is what we're going to call y, but what you do first is you go, well, what appears to be the inside function? It looks like that x squared plus 1 would be an inside function, and you call the inside function u. So so y is a function of x originally, right? Like y of x is the square root of x squared plus 1. And so if I set u equal to x squared plus 1, then I could think of y as being a function of u. Y of u would be the square root of u, right? So by setting a variable to whatever the inside function is, you convert the original function, which was a function of x, to a function of this new variable u. You just have to remember that new variable is really a whole function, x squared plus 1. Well, since y is a function of u, then it would make sense to talk about the derivative of that y with respect to that new variable u, right? Well, if you just saw the square root of u, what would be its derivative? Well, that's u to the 1/2, right? Square root of u is u to the 1/2. So I could differentiate that with respect to u. There'd just be 1/2 x, not x this time, it's u. 1/2 u, and then you do 1/2 minus 1, right? So in other words, 1/2 u to the negative 1/2. So you see in the formula up here for the chain rule, that first term, dy du, we just computed it right here. And the second bit that you need to do is you need the du dx. Well, we've got u setting there, and it's written as a function of x, so we can compute du over dx from that bit. Well, du dx just means, take the derivative of that expression with respect to x, and that'd be 2 times x plus 0. And, right, so now this bit right here in red, we've got here. So now we can just put the two bits together. So putting it all together, we got dy dx. The derivative of the original function with respect to the variable x is dy du times du dx. dy du is 1/2 u to the negative 1/2. And then du dx was 2x. And instead of leaving that variable, like we got mixed variables here, we got a u and we also have an x in that expression, I want to just substitute back in what u is so that I only have one variable in play. So I could write this as 1 over 2 times the square root of, and I'm going to remember u is equal to x squared plus 1. And then I have 2x, so I could just write, well, I'll write the 2x out here. And a quick simplification would make that x over the square root of x squared plus 1. And there's our derivative. So the point of this was to show how you can see what the pieces are in the chain rule formula by making a substitution, by just making a variable, say u. It doesn't have to be u, you can call it whatever you want. But it's kind of conventional to take u to be the inside function. So just remember, always u is going to be the inside function. And then the next thing is you calculate dy du, and then after that you calculate dy dx separately. I'm sorry, du dx separately, and then you just multiply. So that's how it goes with separating it out into that form. So let's just see a few examples of how you do the chain rule. Now on these, I'm going to not make such a big deal out of saying, giving a name to the inside function, whether I call it g of x or whether I call it u. I'm just going to do it. And I always have to think, okay, what's the outside function? Sometimes it's not as clear as other times. Now, how about this first example here? There's one function that's on the inside, and there's one function that's on the outside. Well, it may be easier to think about what's the inside function first. I don't know. I can see, though, that the sine x is inside the exponent of the exponential function, right? You know, another way to write this, you could write this, another way to write e to the something is to write exp of it. So you could write that as exp of sine of x. And when you write it that way, it's like, oh yeah, now it's clear that the sine function is the inside function and the exponential function is the outside function. We know that the derivative of e to the x is just e to the x. So if I want to take dy dx here, I differentiate the outside function. The outside function is e to the, x, but it's got an inside function that I'm going to leave there. So I get the derivative of the outside function is just e to the sine of x. Then I have to multiply times the derivative of the inside function, which the derivative of that will be cosine. So we end up with e to the sine of x times cosine of x. So our inside here was sine of x, and our outside was e to the x. That's what was going on. On the next one, the derivative of y with respect to x would be, okay, I can see that the outside function is the sine function. The derivative of the sine function is cosine, and then I just leave whatever's on the inside there. But then I got to multiply times the derivative of the inside function. Now the derivative of the inside function will just end up being negative sine. So this is going to look like cosine of 1 plus cosine x times negative sine x. See, the chain rule is really not that hard to do in practice. You just have to recognize when do you use it. Well, when you use it is when you've got a composition of functions. One function is set inside of another one. And then once you realize one function's inside, then you should see what's the outside. And sometimes the choice isn't even unique about what's the inside function and what's the outside function. Okay, and sometimes you may have to use the chain rule multiple times. In the next example, you have to use the chain rule twice. So let me show you how that would go. So first of all, that function, you're taking the cube root of tangent of e to the x. There were two ofs there, so that means it was sort of a multiple composition. So I can write that as tangent of e to the x, and then the whole thing's raised to the 1/3 power, right? So it's clear to me that the outside function is raising something to the 1/3 power. So if I want to do dy dx, how do you differentiate something to the 1/3? You bring the 1/3 down, you take the something, and you reduce the exponent by 1, so you'd get negative 2/3 for the exponent after you subtract 1 from the exponent. But then you got to take the derivative of the inside function. But now, if you're going to take the derivative of tangent e to the x, you see that tangent e to the x is itself a composition of the tangent function on the outside and e to the x on the inside, right? So that means I need to use the chain rule again. So I'm going to bring along this 1/3 tangent of e to the x to the negative 2/3. And now I'm going to use the chain rule again. What is the derivative of tangent? Well, we learned in a previous lesson that the derivative of tangent is secant squared. But tangent had an inside function, e to the x, so we got to leave it there like that. And now we got to multiply times the derivative of the inside function of that tangent function. So there was me using the chain rule a second time. And then to finish it off, we just remember that the derivative of e to the x is e to the x. So there you go. So yeah, you may have to apply the chain rule sometimes 2, 3, 4 times if it's an especially compound function. Something that comes to mind to me that requires a lot of applications of the chain rule would be like if you did square root of 1 plus the square root of 1 plus the square root of 1 plus the square root of x, something like that. I've got a lot of square roots and stuff, more complicated stuff inside those square roots as you go. So like there, you'd have to do the chain rule 1, 2, 3 times there. So anyway, you may need to combine doing the product rule with other rules like the quotient rule. Like in this next example, I've got p equals quantity t over t plus 1, all raised to the 5th. Notice I changed the names of the variables. What do you do? Well, you just do it the same way. We understand that the independent variable here is t, and so we still just do what we did before. if I want to do dp dt, I differentiate the outside function. Well, the outside function is raising something to the fifth power, so that would be 5 times whatever's on the inside raised to the fourth. But now we got to take the derivative, we got to multiply times the derivative with respect to t of the inside stuff, which was t over t plus 1. And then to do that derivative, we can do the quotient rule. And the way that works is you take the derivative of the top times the bottom, so you just end up with 1 times t plus 1 minus, then leave the top alone, take the derivative of the bottom, you get just 1, and that'll be all over the bottom squared. And we could do a quick simplification here. That'd be 5 times, looks like we'll get, could write it this way, 5t to the fourth, and then in that fraction over here on the right side of that expression, there's a t and a negative t in the numerator. So those cancel and you're just left with 1 times 1. And then in the bottom, you got t plus 1 to the fourth and then another 2, t plus 1 squared, so you'd have t plus 1 to the sixth. So you could reduce it like that to make it look a little prettier. Now on this last example, we could have taken the more spelling it out route where we say, okay, we explicitly name what the inside function, we give the inside function a name, like maybe you call it u. You could do that, like what do we have there, t over t plus 1 to the fifth. I could say, like, take the inside function here and call it u, so that this is u to the fifth. Then if I applied the chain rule, dp dt, because I want to get the derivative with respect to t, because that's the original variable, I could write that as dp over du times du dt. So that would be adapting the chain rule for this different variables. Notice that the du's, it's kind of like the du's cancel in that when you multiply those two fractions together. What's dp du? Well, you have p as u to the fifth, right? So this would be 5 times u to the fourth from the top. And then what's the derivative of u with respect to t? Well, remember u is t over t plus 1, right? So we'd use the quotient rule and we'd get, derivative of the top, which is 1 times the bottom, t plus 1. Then we do minus top times the derivative of the bottom, that's 1. We just did this a minute ago, right? Over t plus 1 squared. And then you would just substitute back in what your u is. So you'd have 5 times, and then u was t over t plus 1 to the fifth. And then that one expression over there would have reduced to 1 over t plus 1 squared. And then we could simplify that a little further like we did a minute ago and have 5t to the fifth over t plus 1 to the... Oh, I made a mistake there. That should be a 4. Oops. I thought there was something looking weird. Yeah, 5t to the fourth, and then t plus 1 to the sixth in the denominator. There we go. But that's the same answer we got before. It just sort of breaks it down into, like, what's the inside function and giving it a name, u, and then making the outside function looking simpler by making it look like u to the fifth, so you can kind of think about differentiating it more easily. So if it helps you to break it down like that, by all means, please do. But what I've noticed is most of the time in practice for computing derivatives, people do it more like we did here, where we just sort of looked at the whole function and said, oh, that's something to the fifth, so I bring the 5 down, lower it to the fourth, leaving the inside stuff alone, then just immediately jump to multiplying times the derivative of the inside, like we were doing right here. Whatever you feel comfortable with, whatever gets you the right answer, please feel free. A little later, we'll have a whole lesson devoted to doing related rates problems, and in those situations, it's very helpful to break up, like thinking about your derivatives broken up into a product of two different derivatives like this. So there is something to be said for doing that sort of thing and getting good at it, because it is useful in specific real-world situations. At this point, you just need to go practice a bunch of those and get good at it. So I'm going to stop there, and hopefully you have enough examples to get you started. Bye now.